Welcome back to this course on multi-core systems. In this lesson I will discuss two challenges of parallel processing. The first challenge has to do with the limited parallelism available in programs and it relates to Amdahl's law. The second challenge arises from the relatively high cost of communication. I conclude this lesson with some challenges of parallel processing. According to Hennessy and Patterson, the main challenges are Amdahl's malicious law, which is illustrated here on the right, and the long latency of remote access. In my opinion, there are many other challenges such as programmability, portability, power efficiency, etc. But in the interest of time, I will only discuss the first two challenges, Amdahl and long remote access latency. Yes, it's Amdahl's law again. Limitations in available parallelism make it difficult to achieve good speedups, as this example shows. Suppose we want to achieve a speedup of 80 with 100 processors. The question is, what fraction of the original computation time can be sequential? Can you make an educated guess? Well, let's calculate it. Here I illustrate Amdahl's law again. On a single processor, the computation time is 1 and consists of a sequential fraction S and a parallel fraction P. By definition, S equals 1 minus P and P equals 1 minus S. When we have n processors, we accelerate the green part, the parallel fraction, by a factor of n, but we do not accelerate the sequential fraction. So the time will be S plus P divided by n. The speedup is therefore given by the time on a single processor, 1 divided by the time on n processors, 1 divided by 1 minus P plus P divided by n. We can now substitute the given parameters and obtain that AD must be equal to 1 divided by 1 minus P plus P divided by 100. We can do some algebraic manipulation. We can multiply both sides of the equation by 1 divided by 1 minus P plus P divided by 100 and divide both sides by 80 to obtain this equation, which simplifies to this equation and finally to this equation. Finally, we obtain that the parallel fraction must be equal to 99.75%. In other words, to achieve a speedup of 80 with 100 processors, only 0.25% of the original computation time can be sequential. This is quite a challenge. The second challenge I will illustrate with a simple example is the impact of long latency of remote memory accesses. In this example, I assume that the latency of remote memory access is 200 nanoseconds, that the clock frequency is 3.3 gigahertz, and that the base CPI without remote memory accesses equals 0.5. Furthermore, I also assume that all accesses except remote memory accesses involving communication hit locally, and that the processor stalls on a remote access. The question is, how much faster is this multiprocessor if there is no communication versus only 0.2% of the instructions involve remote communication? We can solve this question using this equation. The actual CPI is given by the base CPI plus the rate of the remote request times the cost of a remote request. The base CPI and the remote request rate are given, so the actual CPI is given by this equation here. And the cost of a remote request is 200 nanoseconds. Since the clock rate is 3.3 gigahertz, the cycle time is 0.3 nanoseconds, and the remote request cost equals 666 clock cycles. We can now substitute this value, this cost, in our equation and obtain that the actual CPI equals 1.7. So without communication, the CPI is 0.5. So the multiprocessor without communication is 1.7 divided by 0.5, or 3.4 times faster. This is significant, given that only 0.2%, so less than a single percent of the instructions involve remote communication in this example. This completes this lesson. Thanks for watching. In the next lesson, I will describe the cache coherence problem and explain what multiprocessor cache coherence is. Hope to see you back.